Think I am live. I'm starting. Oh, shoot. Stop broadcast. Forget it. Cancel. Close. All right. Welcome. Thomas Dimitrovich here. Welcome to our Tech 5 o'clock Tuesday. Today, well, Happy New Year. If you, hopefully you started off the new year great. And you're ready for an exciting 2022. I know I am. We are going to have a blast this year. So what I'm going to be talking about today, I want to start a series on power systems design. So what I'd like to do is take a look at various aspects of of designing a power distribution system. I'm going to focus pretty much on commercial, maybe a little bit of industrial, because commercial, I would say in many commercial applications, hey Nihad, 3 times, I know, 3 times today. It's been a busy first day back, so I hope you are doing well. And I know I still have to take a look at our paper. So, but we're talking, I want to talk about power systems design, Nihad. And I want to talk a little bit about some of the decisions that have to be made. And what are the driving factors? And I'll tell you, I've had multiple questions on the topic that I'm going to talk about today, which is voltage. Primarily, I mean, if you think about, voltage, I mean, it's one thing just to say how we design and select equipment based on voltage. Typically, all right, excellent. From our friends from Ireland, welcome aboard. So when you think about voltage, a lot of, most often, you have a design and you just need to pick, so I need 480 volt equipment, or I have a 480 volt system. But if you're starting from scratch, you're going to build a commercial building. Maybe it's maybe it's an industrial building. Maybe it's a commercial building that is a high-rise apartments, will demand maybe certain voltage selection. But a commercial building that might say, for example, have some light industrial. I say light industrial, maybe there's a welding shop, or there's a small manufacturing going on of, maybe they're making widgets. I don't know. They've got some light manufacturing equipment. So the question becomes, what voltage do we provide to a facility, and when do we decide that I need 480 or I need to distribute in 4160, right? So what are the driving factors that says, hey, this is a 4160 application, I need 4,160 volts, for what reason? Why would I be driven to 4160? Why would I be driven to 480? Why can't I just take a 120 volt supply to my commercial building? Everything is in there. Everything's in there is 120 volts, or 240, 120, 240, 120, 240, 241, whatever it takes. So what are the driving factors? And that's what I want to make this discussion on, because what I would love to do is come up with a small commercial building and let's design it. But I've got to figure out. I want to get a real world application example and walk through the design process. So I don't have that project yet that I can get my fingers on, but let's start the discussion around what voltage do we supply for the application. Now, some of my reference books. I need to put a page marker in here. The IEEE Gray book, which is IEEE standard 241. My cover leaves a little bit to be desired. I ripped it at one point but I did save the ripped piece of it. It's supposed to go like this. So it's my gray book. And this one here, what I like about this book is it specifically focuses on commercial buildings. So, but there are some comments in here about industrial for obvious reasons, because again, I think when you get into a commercial building, depending upon what's going inside, you could say, where's the blurry line between commercial and industrial? So this is one of my references. IEEE Standard 241. I have the 1983 book, and I'll tell you, Nihad, I know they're updating this stuff, but I love the color book series, and I know there's duplicative information. I don't really care. I love it. The other reference is my red book, which is IEEE Standard 141. Taking these covers off, I should just throw the covers away. So this is my IEEE Standard 141, and this is recommended practice for electric power distribution for industrial plants. So these two great references. Another reference is my green Industrial Power Systems Handbook, which is my Beeman Handbook, and this is dated 1955. I don't know why I wanted to say 1953. This is a first edition Industrial Power Distribution Systems Handbook, and I love the Beeman Handbook. Absolutely love this book. All right, so those are my references. I'm going to reference these whenever I can or whenever I need to. So first off, let's talk about some of the driving. First, let's talk nominal system voltage versus equipment voltage ratings. I do have this. So, and you'll notice I have a slide in my slide deck for voltage that says I need to add a discussion. You may hear about two different voltages, rated voltage and system voltage, or I would call it nominal system voltage. And I can't forget. Ooh, look what I got. I got my latest copy. I got my latest IAEI news magazine in the mail. Proposed changes to the 2023 NEC. This is these are the titles of what's in here. Don't get caught in the dark. Understanding and applying NEC sections 700.12 and 700.17. We have residential electrical system basics, emergency generators, why, what, why, and how, new questions and answers, the impact of power over Ethernet on standards development into the forest, details of PV systems that inspectors and installers need to know, and then occupational outlook 2021. So there is a lot of really good articles that are in this version. So I'm just looking to see. All right. So I think you'll enjoy the latest copy, your latest copy of IAEI News, IAEI Magazine. Don't forget about it. Our other reference that we'll use today is the 2020 National Electrical Code. So what I want to do is I want to take a look at the definitions in Article 100 on voltage. Because nominal system voltage and rated voltage are very important pieces of the pie. So the National Electrical Code defines, Nihad, it is. What year is the red book? My red book. Now, there are various versions. 1986. My red book is 1986, and I'll tell you why I like this version of the red book, the gray book, and the buff book. As we all know, every edition, we have different chefs, in the kitchen. And one chef might like a little spice. Another chef might like it bland. Okay, I'm a spicy guy. So when I look at the 1980s and early 90s versions of these books, there were some really good diagrams that unfortunately they removed. For example, and I'm just looking to see in the Red Book, there were examples in here that maybe it's the Buff Book I'm thinking of, but there were some good examples that were taken out, and I don't know why they took them out. They were technically accurate, but they removed certain things for whatever reason, and I liked that. I liked what they had in there. So there were some discussions of per unit around motors and all that good stuff, but I really liked these earlier editions of the Red Book, the Buff Book, and the Gray Book. All right, so nominal system voltage as defined by the National Electrical Code, a nominal value assigned to a circuit or system for the purpose of conveniently designating its voltage class. So they gave examples: 120, 240, 480, 277, 600 volts. So these are nominal system voltages. Now, the nominal system voltages in the Gray Book, and this is where things get duplicated. And in a lot of these IEEE documents, you'll see like this, in fact, the IEEE documents, and also, this document here is something that you should have a copy of. It's free, it's a download, but it's Eaton's application guide. In fact, let's do this. If you search for Eaton Consulting Application Guide, so Eaton Consulting Application Guide, you'll see the first link on there is this, and then you can download the entire one. There's a medium voltage selection. This one right here, Power Distribution Systems. This is the document I'm going to show you right now. So go to your favorite search engine and search for Eaton Consulting Application Guide. We called it the CAG, C-A-G. But in this document, in table 1.1, you'll see that there are standard nominal system voltages. Low voltage up to 600 volts. Now it's what? Up to 1,000 volts, right? 3-wire. So you had 600, you have 480, 240. Then you have medium voltage, 2400, 4160, 480, 4800. And if you go back in time, remember, I don't know, I remember I did a Union Carbide plant. I think it was 2300 volts. And that was before those voltage ratings were a little bit before, sort of before they made some changes in how they do nominal system voltages. I don't know what year it was. The Beeman Handbook talks about it. And in the Beeman Handbook, the chapter on voltage is chapter 4. Chapter 4, and there is a portion in here that talks about the 2300 volts and how they moved it to 2400 volts and why they moved it to 2400 volts. Yeah. So in other words, for example, the transformer stepping down from utility voltage often had a rating of 2400 volts on the secondary, and the transformer stepping down to the utilization voltage of 480 or 240 volts had a rating of 2300 volts on the primary. And so it says, because of the design of present-day systems with smaller degrees of voltage drop, judicious use of taps and transformers, the practice is, as evident from table 4.1, which is basically what I'm showing you here, to use the same voltage rating for all transformer windings connected to a given system voltage. This is true whether the transformers are stepping down to this system or stepping down from this system. So what they're basically saying is, what they used to do, and in fact, they still do it. Motors are the only ones that I'm aware of where you'll have a 460 volt motor that you would apply on a 480 volt system. You say, well, why is it 460? Well, it's because the equipment voltage rating is different than the nominal system voltage. Remember, it's a nominal system voltage. That doesn't mean that when you put a meter at any point in the power distribution system, that it's going to equal what's in this table. So whenever you think about equipment like a motor, if I put 480 volts as the system voltage that you would apply it at, but your voltage is actually 470 volts, you would be below the rated voltage of the equipment. If I designed it for 480, plus or minus a percentage, you because of voltage drop, you're not going to be at 480 volts unless you bump things up a little bit. You're going to be something less. So they anticipate that in the rating of the voltage of the rotating equipment, like motors. You don't see that on other applications like lighting, etc. They'll put, this is 277 volt lighting, or this is 240 volt equipment. Your stove is 240. It's rated 240. It's not rated something different. So although some older equipment are rated 115 volts, but typically the only time you get something that's maybe rated 115 or 460, why they rate it that way is there's a motor inside. So the motor is the driving factor. Nihad, you're a spicy guy too. The motor is the driving factor for when when the equipment rated voltage is not equal to the nominal system voltage, something a little less. So in any case, so I've worked on 2300 volt systems in the past. And then here, motors connected directly to the 13.8 volt bus would be rated 13,200 volts. So there's a good discussion in the Beeman handbook on voltage designations, and I think it's worth a read. I'm not going to read it for you. I'm giving you this as a reference. So I'm not selling this book. I don't even know if you can. You can still buy it. I know you can. But this same information is in a lot of forms, right? Our application guide has equipment information and all that good stuff. So you can glean a lot of what's in the Beeman handbook. You don't have to go out and buy a Beeman handbook unless you really want one. But you'll find this information also in the red book and the buff book and the gray book. In fact, in the gray book, you're going to be on in section 3 of at least the 1983 version of the book. I also have the latest copy of it. I have various versions of this book, so I don't know. It's just you get them over the years. So in any case, some of the driving factors, and we just mentioned one, the equipment that you're serving. So if you're looking at a commercial building, for example, let's say you're working on a commercial building and you have appliances, as an example. If you have appliances rated 240 volts, if you have appliances rated for upwards of 240 volts and you try to apply them at 208, you're already at a percentage lower than what they're rated for. So they're not going to perform as you would expect based upon manufacturers' publications, publicized performance values, right? So lower voltages or higher voltages will impact how your designated loads perform. So, and there are some good tables For example, table 23 in this gray book, the edition that I'm referencing right now, it says general effect of voltage variations on induction motor characteristics. Now, remember, this is not variable frequency drive solutions. These are cross the line types of motors. But regardless of where you're at, there are motors in a lot of equipment. It doesn't necessarily have to be a large rotating piece of equipment that you have for, I don't know, manufacturing process. So a voltage variation, say on a this is an induction motor. If you're at 90% of voltage, so it's a 10% reduction, you will decrease the function of the starting and maximum running torque will vary as a function of voltage squared. So you can decrease, if for a 90% variation, you can decrease, that's 10% low, you'll decrease by 20% or 19% the starting and maximum torque. There's no change in synchronous speed. The percent slip it varies based on 1 over voltage squared, and you'll increase the slip by 23% for a 10% reduction in voltage. Full load speed will decrease by 1.5%. And this is, again, a decrease of voltage by 10%. So you had 90% voltage. Your efficiencies will decrease. Your power factor will increase. Full load current will increase by 11%. Think about that. Full load current. I just did a program today for IAEI News Live where we looked at time current characteristic curves, and I showed on SKM how we plot the starting curve, and I apply my overcurrent protective device. And I said, you can adjust your long time pickups to try to get them a little closer to the full load amps to provide maximum protection. But if I'm running my motor at a lower voltage, then I will have a higher full load amps. And if I have my overcurrent device, if I don't have that built into my overcurrent devices, I could trip my overload protection. My starting currents will decrease by 10 to 12%. And they're a function of voltage. Maximum overload capacity, voltage squared, I'll decrease by 19%. So, and then it's the opposite effect if I have over voltages. So voltage selection is important. What's our goal? We have equipment that we have to operate. I want to make sure that it functions. I want to make sure that it functions as designed. So my voltage at the terminals of my equipment are important. I can have a variance of voltage. I can have a maximum and a minimum voltage based upon power distribution system arrangement. What's turned on, what's turned off, what motors are starting. It's important to know your voltage spread. I'll use that as a term, a voltage spread. What's my maximum and minimum for my distribution system based upon how maybe even based on utility maximum and minimums, based on what I'm driving, my loads, how many loads are on, how many motors are starting, etc. Why would a load impact my voltage spread? Because I'm drawing more current. I could have a voltage draw. I'm pulling my current across an impedance, which will increase a voltage drop. So I've got to think about my voltage spread. I have to think about voltage drop. So if I'm coming in at 208 volts and I've got very long runs, I've got a big complex, a campus environment that I need to supply loads throughout my power distribution system across at good distances, I will have to think about my voltage drop for my power distribution system. How do I impact voltage drop? I think I got like 4 ways to address voltage variations, voltage drop. I could, well, 3 ways. I could reduce my system impedance. How do I reduce system impedance? Increase the size of conductors. Larger conductors, lower impedance. Now, that can get expensive, right? Especially long runs. I could put voltage regulators in where I manage my voltage with a piece of electronic equipment, a piece of mechanically electronic equipment to control to provide a constant voltage. That can get expensive. I could provide capacitors, right? Why would capacitors give me the ability to control voltage? Well, I can provide the VARs locally. So instead of pulling, I can reduce my current draw through a conductor by providing the VARs for a specific load at the load. So for example, remember the power triangle, right? So I have, if I am delivering, if I'm at a power factor of 0.7 or 0.8 power factor, which means I have a real and a reactive component. And then I have the hypotenuse, right? So if my angle is large, if I can provide the hypotenuse, or not the hypotenuse, the reactive portion, the non-work related portion of that current locally at the load, meaning I put a power factor correction capacitor there, then I am reducing my angle, which means I'm reducing the current, which means I'm reducing my loss through my conductor. But that can get expensive, right? Providing those capacitors throughout the power distribution system. So, but there are options on the table. The other option is to increase the voltage. So if, for example, I had a university and I have a big campus and I know I have to get power to all these different buildings from my utility, and maybe it's a stadium, I might bring in 4160, distribute 4160 over the long distances for my primary distribution, which would do a couple things for me. It would reduce the size of the conductors, reduce my losses, which the reduction in the size of the conductor would help me from a cost perspective, right? So I instead of large multiple conductors at a lower voltage at 480, I could have smaller, less conductors at 4160, and then transfer that down to a lower voltage. Is putting the reactor in a portion of a branch circuit where an induction load will be conducted be considered? So Tamaki, here's the thing. An inductor, I would say capacitance would help you. An inductor wouldn't. An inductance would reduce the voltage. It would reduce the current. But it would add another impedance. And it would increase the X, meaning my Z would increase because the Z, the longer portion, would get larger. My resistance would be the same, but my X would get bigger, thus my Z would get bigger, hence my voltage drop would get bigger. But what does adding capacitance at the load? Adding capacitance makes my X smaller, which reduces my Z. R doesn't change. the overall impedance, the R and the X, is smaller. So adding capacitance down at the load would help you. I don't believe adding inductance would. That's my opinion, and that's my thought process right off the cuff. I could use capacitors. I can use voltage regulating equipment. Here's the problem though, like if you say, well, I'll put taps on my transformers. Because remember, you have a maximum and a minimum voltage. Right? Now here's the issue. If you do a load flow study and you're looking at your voltages through your distribution system, and you say, well, when I'm running all of these motors, my voltages are lower. And to bump that up, I'm going to put a primary tap on my transformer. I'm going to bump it up a couple percent. I can go upwards of 5%, right? That may help you in the conditions where you have lower voltage problems, but it can hurt you in those times when you are running at the higher voltage. So what do? We put automatic tap changers on transformers, right? And I don't know if you've ever seen those, but they can automatically change those taps based upon parameters, which makes things a little bit more complicated, which adds a little bit more expense and complexity, and in my opinion, reduces reliability. So I can, but I got to be careful if I'm using taps on transformers to bump up or down the voltages, because if I'm working off of a high voltage and I want to bump it down a little bit, what happens when I'm starting all my motors and my voltages are lower? Now I'm even lower than where I'm at. So that can be complicated. I can try to shorten up my runs, but again, you're thinking two things. You're thinking voltage spread, and then the other issue is you call it flicker, right? Those moments in time when things are starting and you'll get like you'll watch your lights dim and then come back again, all that good stuff. So all of these factors play into your voltage selection for your application. Bringing in 4160 and distributing 4160 can help you control your voltage, especially when you have long runs. It can actually help you save money too, because you're reducing the size of the conductors. And we already talked about that. You got to think about what the equipment is that you are driving. So in the back of the gray book, I think it's chapter 11. Or they don't call them chapters. In this version of the book, they call it sections. And I love this. On figure 119, I love it. They have drafting tables. We don't have drafting tables anymore. I mean, there's a whole room of drafting tables in this book. It's just hilarious. Anyway, section 11, I think. Nope, that's not section 11. Actually, I'm thinking of the Beeman Handbook. It's chapter 11. I was thinking, there's some things I like about the Beeman Handbook, and there's some things I don't like about it. I can't. Yeah. Okay. Yeah. So I'm in chapter 11. I can't figure. I got to look at the figure names to determine what chapter I'm in. And they call this load center, power systems, and circuit arrangements. So they call them load centers. So there's like factors on voltage. So chapter 11 in the Beeman Handbook is called load center, power systems, and circuit arrangements. And so what they talk about in here is they term it power distribution. So they'll distribute power at a higher voltage, whether it be 480 or 4160. And then there's utilization voltages, which are typically utilization voltage could be 480. I think at 480 volts, you've got motors, you got motors. You might have HVAC equipment and things like that. But I was just having a discussion with a friend of mine this morning, and we said that I mentioned motors as being a driving factor, and he said you can get 208 volt motors too. So you don't need 480. It's don't use the motor as a reason you got to use 480, because if you need a 100 horsepower motor, can you buy it at 480? Yeah, but you can get it at 208 as well. But again, that's when you have control over all of the equipment. Voltage drop, I think, is a primary consideration for bumping up the voltage. The amount of load. The amount of load that you're drawing may require a higher voltage. Because again, you're at a cost. You got to think about the cost, the size of the equipment, the cost of the equipment, including the conductors, voltage drop, etc. So if you can distribute at a higher voltage, power distribution system, yeah. Do we often see reactors inside the power distribution? So thank you for addressing. How about inserting reactor in series to inductive loads to prevent other loads from getting exposed to the instantaneous voltage drop? Ah, I see. You're talking about transient voltages. Yeah, I think that's what you're talking about, Tamaki, is the transient voltages. Yeah, you want to dampen the system to address the transient voltages. I'd have to think about that one a little bit. I know of people that apply things that way to stabilize, because what does an inductor do? It slows the change, right? I think you're going to think about tuning your system as well. But it would impact your voltage drop. If you're applying those, you really got to think about what I think you should do your voltage analysis to make sure you don't have any issues. But I'd have to do a little bit more research. I've not applied those. I've not applied those. I don't have the background for that one, so I have to put some thought into that one, Tamaki. But that is a good point. Inductors. Transient. Put a note on that one. I'll do some homework and see what I can come back with. Good question. So when you need to distribute energy across a facility, the higher voltages will be an advantage. Smaller conductors, lower voltage drop, less voltage drop. I mean, why does a utility pick 138 kV? Because of voltage drops. I mean, they transmit at these high voltages. In fact, on DC side, I remember Mr. Selvaggi, my professor in school, he was researching superconductors, because the big concern about distributing energy across a country and long distances is voltage drop. So you want to be able to address that. So higher voltages can help you in that regard. And what's nice with the Beeman handbook, now you can't use their cost, but so it says, so they talk about distributing substations, so transformers, right? So if you think about your total load, if you have more load than you can handle from your service equipment, or distributed loads, you'll want smaller transformers in the facility to provide power for either various locations or various types of equipment. And that can help you in reliability as well, because if you want to build a reliable power system, multiple feeders to an area, and even if you're transmitting it down from say 4160 to 480 or 480 to 208, you can do that in multiple locations to break the system up a little bit. So if you have to take a transformer out for whatever reason, you're not taking a large portion of your power system out. And they talk about different costs between, the way they used to do business and the way they do business now. And you can't, they do percentages, but you can't use a book from 1955 to think about costs. They say a power system from 13.2 kV incoming line to the plug-in busway would cost install about $143,000. That's in 1955 money. So be careful there. But I think the basic principles are true. And they just talk about voltage drop in here. So, and then distributing your energy. So I would say the higher voltages, well, typically the big motivator will be large distribution systems, heavy power usage, and voltage drop. That's the major concern, I believe, is voltage drop. But there are many ways to skin that cat. So, and then if you did a 4160, say you did 4160, or even if you did 480, you can design the system from a reliability perspective. You can use the radial, the loop, all that good stuff in your power distribution system to increase reliability. It'll increase some costs, but you'll get the gain out of reliability. All right, so voltage, radial arrangements, all that good stuff. So your system voltages, you have system voltages, and then you have utilization voltages, your ratings of equipment. What else? You have your high voltage, your ultra high. All right. So this is a good reference for you, though. I will put I have a link. Where did I have my link? I searched for it. Here it is here. I'm going to put the link in the chat box. Control C, not Control V. Oh, so keep in mind, reactors resist the flow of VARs. It's true. So if you have high inductive loads on the load side of the reactors, not being able to pass VARs will significantly contribute to additional voltage drop. It's exactly my point. That's what I'm saying. You have to really be careful and do a voltage analysis when you are applying inductors, because remember, it's you're taking a triangle. Your power factor is going to go like this, and your hypotenuse gets more. So you're adding more impedance to the system, and that will impact voltage. And you may address the fluctuation issue, but you may now have a different issue. So it's a balance. I mean, I don't believe there's any silver bullet for any of these things. When it comes to a system, you have to really do an overview. Now there are there are probably engineers out there that say, I never look at voltage and I never think about it. I just design, I do commercial power systems, or I build McDonald's on a daily basis. I'm not worried about, I know I have this type of equipment. I got 240 volt loads. I got 120 volt loads. I get, 240 volts from the utility. I'm fine and dandy. Yeah, that might be true. But when you get into a larger commercial application, like say a campus environment for say a school or a healthcare environment, you might have other considerations that you need to think about. Distributing energy in the location. I know a lot of industrial plants that I've been into had 4160. 4160 seems to be like the de facto. They had 4160 substations, and then they piped it down to 480 because they had a lot of 460 volt motors or 480 volt equipment. And then they would pipe that down to 208 to 120 type applications for single phase, or 277 volt lighting. That's the other consideration. If you've got the industrial, commercial, and you're using 277 volt lighting, then you got to think about that in regard to your voltage. That might be why you need your 480/277Y systems. So the selection of your voltage, if I would sum things up, the selection of your voltage is going to be based upon utilization equipment, what you're driving, voltage drop considerations, so the size of the campus, how you're moving energy from one side to the other. Also the utility. Utility may tell you, look, we provide 208. That's it. Live with it. And you got to figure out how to deal with that. And if you have to step up the voltage, you're going to have to do buck boost transformers. You're going to have to put your 480 volts on the secondary instead of on the primary, 208 on the primary, and then deal with applying transformers in that application. So the first step is going to be, what does my utility, or what can my utility provide me? And then if the menu is wide, then you say, okay, now what is my application? If I have a large campus, I might want to distribute 4160. Do I have qualified people to work on 4160 or be able to deal with 4160 in their application? Does my customer want 4160 on his campus or her campus? Maybe they feel more comfortable with 480. So you've got to take your customer into consideration and the application. So think about the loads you're going to serve, voltage drop, voltage variances, and your transient voltage, your flicker, so to speak, quote unquote flicker. And the code. So the code defines nominal system voltages, which is again not related to rating of voltages. They also they define voltage to ground. They don't define rated voltage. They define voltage of a circuit, the greatest root mean square RMS difference of potential between any two conductors of the circuit concerned. So, and remember that what you measure may not be what you get. And also remember that a transformer is going to have, say it's 4160 to 480. That's no load voltages. The secondary, there you think about the transformer secondary. If you had 4160 on the primary, it may not be exactly 480 on the secondary. You're going to have a percentage lower just from the losses, the voltage drop across that transformer. There is an impedance in there that you need to think about, in addition to the percent Z on the secondary. It's not going to be a 4160 to 480. When you load it up, you're going to be adding to that loss. So, and then you add the conductors down to the load. So, and the length of those conductors. Now, length of the conductors, voltage drop. There are tables. There are a lot of tables out there that you can use. You don't necessarily have to do voltage drop calculations for everything. You can leverage voltage drop tables to get you in the ballpark. And I'll tell you what, they're pretty doggone accurate. So you can, with estimated load currents, impedance of the conductors, you can figure out what your voltage drop is going to be based upon lengths. So, and power factor as well. And remember, power factor correction down the load can help you with that voltage drop. But again, remember it too, when you start applying capacitors in a power system, you've got to think about power quality, your series resonance, your RLC circuits, right? So inserting a capacitor into a power distribution system could present a challenge. All right, so and then you have to think about, what does voltage variation do to your load? It'll impact different loads. It'll impact loads differently depending upon what they are. Induction motors, we already talked a little bit about induction motors, heaters, lighting, all that good stuff will impact the voltage ratings, or the voltage will impact the performance of the loads. I guess the like for a motor, your most significant, I think, if I would hazard a guess, the most significant impact on a motor would be your starting torque. Your starting torque, you're going to increase your temperatures in your motor, you're more heating, things like that. So the rating of the voltage, the rating of equipment is based upon the voltage on the equipment. And you need to determine what the voltage actually will be in your power system through calculations. And I think motors are the only thing you're going to apply on medium voltage. From a load perspective, I can't think of another medium voltage load. By far, if I would hazard a guess, I would say you are, from a load perspective on medium voltage, you have a higher chance of it being a motor than anything else. I won't say it's the only medium voltage load, but I'll say that it's probably the most prevalent. Your electronic equipment will be impacted by voltage and voltage transients, to Maki's point. So there are other ways to address the need of an end product. If an end product, if a load is sensitive to the voltage that it is operated at, you're probably more likely to be successful if you apply voltage, trying to think of the right term, voltage conditioning equipment. You can buy like a UPS type of thing that controls the voltage within a tolerance for the load. Sensitive electronic equipment, good example. Put those puppies on an isolated system, on a UPS driven system, and voltage regulated system. You can control the voltage and the tolerances to that equipment. So, as opposed to a brute force method in using other components. So your cable drop, you understand your voltage drops in your system will help you understand the voltages and the impact. Motor starting studies, that's another thing. If you have large motors, you're going to want to do a motor starting study to understand the impact of starting that motor at various portions of the day, to understand the impact on the voltages for the entire power distribution system. I know we had I think it was an automotive facility, very large automotive facility I was involved with. And we did a motor starting study. They had a brownout, so to speak. Relays dropped off, all that jazz. And they recognized that they were doing starting motors, large motors, all at the same time. And they had to stage their operations. So they talked to their operations guys, said, listen, if you're going to run your test, you can't run that equipment. You have to run it at a different time of day than this department, because they're running their equipment and starting these large motors. You may not be able to start all those motors at the same time. So you've got to understand, especially large motor applications, that's more of an industrial application or a heavy commercial application. Heavy commercial, what does heavy commercial mean? I don't know. It's a term I just made up. And in my mind, a heavy commercial application is a commercial building that has a lot of maybe a semi-manufacturing facility. It's when I think of industrial, I'm coming from Pittsburgh, Pennsylvania. When I think of industrial, I think of a steel mill as an industrial, a Ford facility, a General Motors, a Chrysler, PPG, making glass, industrial. I wouldn't consider that a commercial, but maybe a commercial building like our experience center. It's a commercial building, but we got a lot of stuff in there, right? We're driving motors. We're doing a lot inside that. We're manufacturing circuit breakers inside that structure, or remanufacturing circuit breakers. So it's light manufacturing. So I call it a heavy commercial. I don't know why, but I just make stuff up. Make it up as you go. That's what I would say. So understanding your voltage and what's the driving factor for picking your voltages, loads, distribution, how are you going to distribute, how the length of conductors, the length of the size of your campus environment. Those are the major reasons. And I would say 4160 is one of the most common voltages that you would see in these applications. I just need to get rid of a post. So bear with me. I'm going to go to YouTube Studio. And I'm going to go to comments. Nope, not comments. I have to actually go to my live feed. Your channel. And I am live. Comments. Oh, there it is. All right, so there it is. And remove. Perfect. Remove. Okay. So, my references. If it's a commercial instruction, use the buff book or the gray book, Beeman handbook. Let's take a look at the red book. Red book on voltage. And what's nice in the red book. Now this is an industrial. In the red book, they've got chapter 2, and this again is 1986 edition. Sorry about that. And that is one of those, you know what, forget it. System planning. So they have, again, you have your system, your reliability analysis, all that good stuff. They talk about voltage regulation. Poor voltage regulation is detrimental to the life and operation of electrical equipment. Voltage at the utilization equipment must be maintained within equipment tolerance limits under all load conditions. That's why it's important to understand your maximum and your minimum voltages that you can expect in a power system. You don't know that in the design phase. I mean, you can estimate that in the design phase. You can model your power distribution system in your SCAMS, EDSA, Easy Power, whatever your flavor of choice is. Yeah, Nikola Tesla. Now, you know what this was, Nick? This is, and I know this comes from a Pittsburgh number, but it's usually either your auto insurance is expired, but the ones I really love are the Comcast ones. So I try to keep these guys on as long as I can when I have the time. If I'm sitting at my desk and I'm doing some mindless, they answer up, and what they'll do is they'll say, we have to update your router. And I say, okay, do you? He said, yeah, go. They tell me, go to your router. And I give it a pause. And he says, do you see blue lights flashing? There's always a blue lights flashing. And I say, oh yeah, I got blue lights flashing. Is that a bad thing? And they say, oh yes, that's a bad thing. So we're going to update your router. And they'll ask me to open up my computer and go to a website and type something in to start. And I just keep them on. I play dumb, like, what's the Windows key? Does it have a W on it? And I try to keep them on as long as I can. And now I hardly get any of these calls. I got them so mad. They called me back and left me a voicemail cussing and swearing me and calling me names because I kept them on for at least an hour and a half. I'd put them down. So my goal when I get those calls is to try to unburden all of you out there and keep them on as long as I can. So a load. So planning. So what's nice about the red book in the chapter 2, they have system planning and considerations. Load calculations are important, which what I'm going to do is I'm going to pick a power distribution system, one line diagram, or actually we'll pick a commercial building, and we'll just walk through the design phase. And what I'll do is I'll try to find one that is a real world application and walk through the quoting process, the layout process, the calculations we do before we buy anything, how we go out for bid, all that good stuff. And I think that'd be a fun exercise. And maybe that's what we do this year, is we focus on that type of a program. But voltage consideration, that's what we're talking about now. So the voltage, so the following procedure. So you have to do your load survey. You have to do your demand, your peak loads, your maximum demand load, and what types of loads you're serving obviously plays an important role from a voltage perspective, right? And then they talk about the layout of the system, whether it's a simple radial system or a loop system, primary loops, primary selective system, all that good stuff. So you have to think about your reliability. In most commercial buildings, you say, hey, look, I'm coming in at the main and I'm going to distribute. I'm not worried about a loop system. But if I have a campus environment, multiple buildings, I may want to do a loop system so that I can take a building offline and not impact another building. Or if I have a problem with a transformer, I don't have any buildings going down, I can limit my outage from a reliability perspective. You got to think about, what are you doing in this campus environment? Is it what's important? So, for example, if I'm Penn State University, or I am, I'm a university period, and I have a football field, a baseball field, and then I have my campus environment, I may say, look, reliability is critical. I might distribute 4160 in a loop system so that I can make sure that my stadium is up and running regardless of what goes on in my system, right? So there may be reasons why you pick a certain type of distribution in addition to the voltage for your system. So what they say in 2.3.5 for voltage, it says, select the best voltages for the various system voltage levels. The most common utilization voltage in the United States, utilization voltage. So here's what you got to think about. There's utilization and then there's distribution. The most common utilization voltage in the United States, industrial facilities, is 480 volts. Other voltage levels depend upon motor rating, utility voltage available. We talked about that. Total load served. We talked about that too, because the more load, you may drive your voltage up. Potential expansion requirements, voltage regulation, and cost. So I may, like I say, I might go to a higher voltage for smaller conductors because of my runs. Chapter 3 is a guide for correct voltage selection. So let's take a look at chapter 3. What's funny is I've been through these books so many times. They talk about voltage sags and swells. Another good reference for electronics is the Emerald book. The Emerald book. I'm not sure of the standard number. That will get into sensitive electronic equipment. Oh, yeah. So chapter 3, voltage considerations. Voltage considerations, understanding of system voltage nomenclature. So this again, system voltage, nominal system voltage, maximum system voltage, service voltage, utilization voltage. Those are all your different parameters that are important to understand for your power distribution system. And again, if you think about it, if you've been in the business enough, you may say, I don't think about this. You're getting granular, Tom. Well, for you, I'm getting granular. For somebody coming out of school, going into power systems design, it's all new to them. They've got to consider these things. But for the seasoned veteran professional engineer, they've got moxie. They're polished. They understand all of the details. So application voltage classes, they got standard nominal voltage. We talked about all the different standard nominal voltages across the United States. It'll be different for Canada. It'll be different for our friends in Japan and our friends over there in Ireland. Voltage systems outside the United States, voltage systems in other countries generally differ from the US. For example, 416 240 is widely used as a utilization voltage, even for residential services. Also, the frequency, 50 hertz instead of 60 hertz, which affects the operation of equipment. And there's a nice table in here, standard nominal system voltages and voltage ranges. All right, so, and as you go through this book, voltage is control and electric power. So principles of power transmission and distribution in utility systems, and then you'll get to transmission for your customer-owned facility. Electrician from the Caribbean. If anybody wants to get in touch with me, you can reach out to me. Send me an email. Thomas A. Domitrovich at Eden.com. Or you can visit my website, which has a link, www.thomasdomitrovich.com or www.tdomitrovich.com. All those different ways you can go out to my website, and there's a link on there to contact me. Send me a note if you have a question. I'll do what I can to help you. Voltage profile limits for regulation. So system voltage tolerance limits. Allowable voltage drops. System voltage tolerance. So you have to understand your voltage tolerances for all of your different equipment. What to expect from the utility. All right, I'm just looking to see non-standard nominal system voltages. They talk about using taps. You got to be careful with transformer taps, in my opinion. The reason I say that, if you're doing a tap because you're trying to address a voltage sag, a minimum voltage issue, then you could be exacerbating a problem when you have a maximum voltage. So you have to understand your maximum and minimum voltages based upon system operation. They have tolerance limits in here, tolerance limits for lighting circuits. So if you have 480, 277, transformer tap is normal. If you're a 480, 468, 270, you're going to do a plus 2.5%. 456, 263, plus 5%. Tolerance limits for low voltage three-phase motors, plus or minus 10%. So the preferred utilization voltage for industrial plants is 480, 277. I would say for a commercial building, you're probably 208. Unless you have some sort of manufacturing going on where you need 480, you're probably 208 volts is the commercial building. I don't know if there's something in here that says that. That's just me talking. Do you have an opinion? Hey, thanks to Mr. Solomon or Ms. Solomon, whatever. I'm not sure the gender of Chinua. I don't know. So I would say for commercial, you're probably at 208. Voltage systems and other kinds. So this is nominal system voltage. These voltage and their associated the nominal system voltages, blah, 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 application voltage class. I'm just seeing if there's anything in the commercial building book that says what is typical for a commercial building. My opinion is 208. But I'd love to know your opinion. All right, Mr. Solomon. Thank you, sir. Sorry about that. It happens. So there are some names. I just don't know the gender, so I don't. So I would say 208 is probably very common for a commercial building. And in an industrial is a little different. The preferred utilization voltage for industrial plants is 480. Three-phase power, 480 loads are connected directly to the system at 480 volts. So if you have, again, you have your 480 volt equipment and gaseous discharge lighting, 277. If you have 277 volt lighting, you're going to need 480 volts. But where do you see 277 volt lighting? You probably see that in a commercial building, in my opinion. 208 is probably the most used in the commercial application. For small industrial plants supplied at utilization voltage by a single distribution transformer, the choice of voltages is limited to those the utility will supply. However, most utilities will supply most of the standard nominal voltage listed in ANSI C84.1, with the exception of 600 volts, although all voltages supplied may not be available at every location. This is the US. The built-up downtown areas of most large cities are supplied from secondary networks. That's going to be 208. Like your new, I believe your New Yorks and whatnot are all 208. But most utilities now provide spot networks at 480, 277 for large installations. So most of the commercial buildings are going to be your 208 systems. And you can control your voltage drop by how? Lower impedance, busway. Busway is a great, you know what I call busway? A high efficiency fault delivering system. So if I want to get from the bottom of a building to the top of the building with the minimum voltage drop, I'm going to use busway. It's the lowest impedance from a 480 volt distribution system, 208 from a 208 volt distribution system. Busway is superb for that. And you see that a lot in high-rise buildings. So Sorab Alama Jose, good morning. I usually used 380, 220 volts for commercial buildings. Sorab, where are you at? 380, 220. Is it 3 or 480? Or what do you mean by 380? Or what's your location? Give me your country of origin and where you operate and function is. And is that, I'm just going to look at my voltage table here. I got 480. I don't have 380. Maybe you need 480. No, it can't be 480. The 240 is familiar. I don't see 380 in the standard voltages, but anyway, let me know if you meant 480 and 220. Caribbean. They hardly go by code, but from what I came across you in an electricity program, you guys taught me a lot. Hey, I'm glad you learned something. That's good feedback. I really appreciate it. And you remember, so the code is a bare minimum requirement, but a lot of what I talk about are basic fundamentals of power systems engineering, which might be above and beyond what the NEC requires. So. Anyway. All right. Substation is supplied by the industrial plant. Most utilities have a lower. Okay, we already talked about the utility is going to be a limiting factor. Voltage ratings and low voltage utilization equipment. Utilization equipment is defined as electrical equipment that uses electric power by converting it into some sort of work, right? 120 volts, 208. I'm from the Philippines, 400, 230. All right. So Philippines, so outside of the US, the voltages can be quite different in their applications. What frequency are you in the Philippines? Are you 50 hertz or 60 hertz? Probably 50. I don't know if you're 50 or not. So that's a clue. Yeah, Nikola Tesla, right. Could be Asia. You know, that's the thing. We are international. 480, 240, 208. Yep. 50 hertz. That's what I figured. 50 hertz in Ireland. 400, 230. Wow. Mr. Tesla. Wow. And then in the red book, they talk about the general effects of voltage variation. So voltage, again, you want a constant voltage. You want to be within the tolerances of your your utilization equipment. Gustavo, Costa Rica, 480, 240, 208. Excellent. Gustavo, what's your frequency? 50? I think you're 60 hertz then, Costa Rica. Yeah. Sorab, Alamo Jose. Excellent. 60 hertz. All right. Excellent. Excellent. 60 hertz. Gustavo, 60 hertz. That's what I figured. Fluorescent lamps, unlike incandescent lamps, operate satisfactorily over a range of plus or minus 10% of the ballast nameplate voltage rating. Now, here's the thing. On some of these, when you go low enough in the voltage, you can drop the load out, and then it takes time to get it back on again. So your voltage fluctuation variation is very important. Tamaki in Japan, 50 hertz and 60 hertz are in the same nation. That's interesting. Nikolai Tesla is in Pittsburgh, Pennsylvania. We got to do dinner one day, Nick. Send me a note. I'm in Pittsburgh. We were just, Bobby Joe and I just went to, we went to Newsstand. I bought a curio cabinet. We were looking at another curio cabinet. So we drove out to, I can't think of the name of it, out past Newsstand. About a nice 50-minute drive. But we ate down at the, on the way back, Nick, we ate at the brew house. Pittsburgh Brew House, I think it is. Remember, it's the church. No, it's the church. The church. Well, the church that's that makes beer, microbrewery. I can't think of the name of it. Anyway, let me know. We'll have to do dinner or something. All right, capacitors. Reactive power output of capacitors varies with the square of the impressed voltage. A drop of 10% in the supply voltage, therefore, reduces the reactive power output by 19%. Oh, you're in Lawrenceville. Okay. And where the user has made sizable investment in capacitors for power factor improvement, loses the benefit of almost 20% of his investment. So, yeah, Nick, you got to let me know one day. We can get together, do some dinner. Solid state equipment. So there's a lot of discussion in the Red Book about, and in the Gray Book, and in the Beeman Handbook. When we talk about voltage, you talk about the performance of the loads and why it's critical to keep your voltages within tolerances. Improvement of voltage conditions. Again, they're going to talk about raising the voltage for the long haul, power factor correction, reducing your impedance, all those things that we talked about. Voltage control. There's equipment out there now that'll maintain a constant voltage for you. It's incredible what they can do. Measurement of phase voltage, unbalance, effective phase. Another phone call. And it is 6:18, so I'm going to be getting off anyway. I'm going to give him a call back. Voltage dips and flickers, depending upon utilization equipment, how you're operating it. So total dip is a sum. So there's a lot of great information in chapter 3 for voltage. Now, Tamaki brought up, we'll all go out. Yes, I'm good friends with Nate, Dan Carnevale. Oh, Nate Carnevale, yeah. Yeah, we ought to all get together. That'd be kind of cool. As long as I can bring Bobby Joe. Harmonics are so inductive reactances vary directly as the frequency, so that the current in an inductive circuit is reduced in proportion to the frequency for a given harmonic voltage. So harmonics play a role, and it's in the voltage. Where harmonic interference exists, the regular measures of increasing the separation between the power and communication conductors and use of shielded communication conductors should be considered. Capacitor banks magnify the harmonic current. The capacitors should be changed to suitable types or removed. So when you're trying to fix voltage drop issues, you could create other problems. Harmonic issues, resonance issues. You can hit the series resonance and wreak havoc on your power distribution system. Calculating voltage drops. So there's a lot of really good information in here. So, but my goal of today's session was to raise your awareness on some good reference materials. These are my 3 key books. You can't see the Beeman Handbook because it's green and I got a green screen. Red Book, Gray Book. my Beeman handbook, the National Electrical Code, to an extent, it's a definition. But when you, outside of an informational note in the National Electrical Code talking about voltage drop and a percentage, you're really into providing a power system that performs well for your client when you're laying out your system. Steve Cavalis from New York, thanks for the link for the consulting application guides. Nice resource, great. Thanks for providing these. Excellent. Thank you, Steve, for joining in, and Mr. Tesla. All right, so I've babbled for about an hour and 21 minutes. I think I made a little bit of a dent. What I am going to do is I'm going to try to find a commercial building, something that has been built and designed already, that I can something not huge, and we can use as a basis to walk through the design process. Before you even break ground, you need to make these decisions. Like, what voltage do you need for the application? And I tried to address that. Your loads are critical. Voltage drop considerations are critical to make sure your operating voltages are right. The size of the distribution, the facility, what do I distribute my energy at might be different than my utilization voltage. So all of those play a key role in the costs trade-offs. If I have long runs, I might be able to use smaller conductors, which will reduce my cost, but use medium voltage equipment. And the offset, they may offset each other, but it may be a lot less expensive to do a medium voltage distribution and then ramp down to either 480 or straight down to 208 for utilization equipment. But the reason we would typically raise the voltage, again, in my opinion, is to transport power across those across a campus. Mr. Solomon, I have to send me these books so you can study the codes, because it's important to know these things. It is. I can't send you my books. I just can't do it. These are. You know why I can't? Because look, they got my name inside. I write my name. I had a book. And I used to say it was stolen, but I don't believe it was stolen. I believe it was borrowed, and it was never returned. So I usually lend my books out. I used to have all of these books at work. Now this is my work. So, but in any case, that's where I'm at. All right. I'm going to end this session. I hope you got something out of this discussion. I appreciate people chatting it up. Don't forget to subscribe to my YouTube channel. Check out my thomasdimitrovich.com. You can subscribe there. I'm going to do more with that this year, trying to provide resources for everybody as we work and learn together. And Nick, let me know. We'll have to all do dinner one day. That would be awesome. I'd look forward to that, coming down to Pittsburgh. Thank you, Mr. Smith. Mr. Smith, and you're the one who said let's pop the clutch, right? So I appreciate you dialing in as usual and as well. So thank you for all what you do. No problem, Nick. No problem. Thanks for everything that you guys and gals do for the electrical industry and electrical safety, and for tuning in. So we're going to get better this year. Pop the clutch. That's it. Pop it. So don't kickstart a clutch. You kickstart a Harley Davidson or a thumper, but you pop the clutch. All right. So this year I'm going to find a small power distribution system, and we're going to smash that like button. And remember, if you're going to hit thumbs down, you got to hit it twice. So this year I want to focus on power systems design, which will include some analysis. Happy New Year to everybody. Happy 2022. Get 2021 behind us, and especially 2020 behind us. And, I thought COVID was going to be gone, but it's ramping back up again. Don't forget, too, Electrical Safety Workshop. Hopefully it's going to be in person, but we're working on that. So you're not going to want to miss that. And we will have a version of the electrical safety workshop. You can register. If you're not going to attend in person, you can view the videos of the presentations. And if we end up going virtual, then anybody can attend. So be mindful that the 2022 electrical safety workshop planning is in phase. And Thursday, I'm going to do a live session on Thursday. We'll get more into the meat of this discussion for power systems design. And I'm going to do a Q&A Friday. So I've got some questions piling up already. All right. Shinwa, Gustavo, Nikolai, Tamaki, yes, work and learn together. Thank you. And thanks for all that you guys and gals do for the electrical industry and electrical safety. So remember, be safe. And remember, stay healthy. Okay? So I am going to sign off for now. I'll see you Thursday at 5 o'clock p.m. Eastern. We'll have another session. Probably power systems design. All right? Okay. Thanks, everybody. Take care. Stay safe. And remember, please stay healthy.